Okay, thank you. Thank you very much, everyone, for being here to this first keynote of this fourth School on Quantum Computing. We are really honored, we are very honored to have with us Dr. Jørgen Ellegaard Andersen. I thank you very much for your willingness to lecture this note. So I'm going to present Dr. Jørgen Ellegaard Andersen. He's professor and chair of quantum mathematics at the Danish Institute for Advanced Study, and he's the director of both the Center for Quantum Mathematics and SDU Q-Hub at University of Southern Denmark. He holds simultaneous a Simon Collaborator grant and an ERC-Synergy Grant, the two most prestigious grants in America and Europe, respectively. He's further the founder and CEO of the spin-off company Qpurpose, which produces quantum software to a broad range of the largest Danish and international companies. So we have really an exceptional person, and we're looking forward to listening to your conference. Thank you very much, Jørgen. So please, you can start whenever you're ready. Thank you.
Thank you very much for this very kind introduction. And hello, everybody. Pleasure to be able to join you here online. And maybe I thought I would start with a little bit about my background. So my background is really that I did my PhD in Oxford, and I've basically been working on quantum theory ever since. Right after my Oxford degree, I went to California and became a professor at the University of California, Berkeley, where I was there for about 10 years. Following that, I was a Clay professor at Harvard University for a short period, because all of a sudden, really fantastic opportunities arose in Denmark. You could actually acquire rather large grants in Denmark and run really very big research activities. So I went back to Denmark and got one of the biggest grants you can get in Denmark and ran a big center there at the University of Aarhus in Denmark. Towards the end of that was a temporary 10-year thing. I was lucky to get an ERC-Synergy Grant. And once you get those, rectors around Europe get very interested in you. And so I got lots of offers, also from some universities mentioned earlier. But somehow University of Southern Denmark gave a fantastic offer. They said, we will really build a permanent center around the activities that you represent. And so I decided to go there. That's where I'm now. And the positions was just mentioned that I hold there now. So maybe I tell you a little bit about the center that we have there. It was very important to me to build up really an elite with really world-leading scholars to establish a very strong mathematics department or a center. And so I hired an international advisory board, of which there are 6 Fields medalists on the board. And they have really been instrumental in actually helping me set up the center. And so if you look over here to the side, we have sort of a hybrid setup, which I consider extremely important, because this hybrid setup has on the one side very theoretical and completely pure science-oriented activities within the math that underlies quantum theory. That's what we call quantum mathematics. And then on the right, you see actually a company, Qpurpose, that was mentioned before, that we have created 3 years ago. And then there's a huge overlap in the middle, and that is totally deliberate. So a number of people are actually working on both developing the mathematical foundation of quantum theory, and at the same time also developing very interesting applications of this into industry. And so the intersection in the middle is really deeply focused on developing quantum algorithms and quantum software and actually applying it to real-life problems. And to the right, you see a sample of the customers that we have from some of the leading Danish companies. I can tell you in the meantime, something like Rolls-Royce and Airbus has also joined the list of customers. But to the very left, you have really pure mathematicians who are not interested in quantum computing, but who really focus on the deep mathematical theory behind, quantum theory, as I used to do myself. And I think this mix is super, super important for being a success in actually developing high-level applications for these rather big companies, because this gives us a depth in mathematics that they really cherish. And I'll probably try to see if I can come in and say something about that a little later. We've acquired quite a lot of grants to run the center. We get some large grants from the university, but it's also very important that we can gather grants. And in fact, in Denmark, there is a really fantastic setting where a number of these big companies actually already understand that it is super important to support science, both basic science and applied science. So although we have some from the ERC, as you can see, and from the European Commission and from the Danish government, the Innovation Fund, we also have a number of different grants from well-known companies like Novo Nordisk, which is a pharma company, the Willem Foundation, who makes these, maybe these roofs, these windows that tilt in the roofs, they are actually made all by the Willem company. And then maybe you all know Carlsberg, that's another Danish company. I should add here in the end of our presentation of the center that we have actually just started. We have just admitted the first cohort of new students. It's a master education in quantum computing. I welcome you all to sort of have a look at this in the future. We will be running this every year. We will take in a new cohort the next summer. So this is an education which is dedicated entirely to quantum algorithms and quantum software. So not hardware, but software, and it will cover all aspects of these things. If you are so lucky that you are from Europe in this connection here, actually you will be entered into the university for free, and we will even give you a salary of about $1,000 a month. If you are not from EU, then you have to pay. But okay, let me push on. So quantum computers. I mean, quantum computers really is at the brink of exploding, and it has received considerable political attention. So clearly seen here, Biden was visiting, so this is a little bit old, but it's about a year or two ago, he was visiting the IBM lab up north of New York City, where IBM has its plants. I've been up there also. It's a very, very interesting place to visit. And, the entire world is actually putting in large efforts from the governments in spending on developing quantum technology. So this map here only shows investments from the governments. It's from 2023. So it has only risen since then. Maybe it's worth noting that, the biggest spender on this is actually China. Spending about maybe close to 4 times more than the US on this. So really serious efforts are going in there. And then you see also various different kinds of funding around Europe, Canada, and so on. And since I'm from Denmark, maybe you allow me to spend just a few minutes on what we're actually doing in Denmark. So we have actually created a Danish strategy for quantum computing and quantum technology. It has somehow enabled the government to put aside 1.2 billion Danish kroner to support these activities. It is primarily going to hardware in the beginning, but there's also initiatives for quantum software. And we are pledging with the government to actually increase this, because we think that it's becoming increasingly important to supplement strong activities on hardware with quantum software and quantum algorithms. The Novo Nordisk Foundation, which is really a major player in Denmark. Novo Nordisk company is a huge company in Denmark. It used to be the biggest company, but since the stock price tumbled a bit lately, it's not longer the case. But it's certainly the largest foundation in Denmark. It's about the size of the Bill Gates Foundation, the Gates Foundation. So it's really a big player also internationally. And they have actually pledged 1.5 billion for hardware, which they placed at the Niels Bohr Institute. And there's a huge development to actually build actual quantum computers. The aim is to have a 12-year project, which should complete, if successful, a quantum computer with 1 million qubits and capable of running enormous amounts of gates on these in 2034. You'll see how this will pan out. They've also invested some in sensing. And also the Novo Nordisk Holding, which is the holding company of this company, has put a lot of money into investment in quantum computing companies, startup companies, and so on, both in Denmark and internationally. So Denmark is a small country, but I think we are punching above our weight when it comes to quantum. Of course, one of the founders of quantum theory was Niels Bohr, who was born Danish all the way. He created the Niels Bohr Institute in Copenhagen, and that has been super influential in the development of quantum understanding of quantum theory all along. And this has somehow meant that we actually the country in the world per capita with the largest number of PhDs in quantum. Of course, there are much bigger companies or countries out there, so we are not the largest in absolute numbers, but we are per capita. Now, what is actually the state right now of quantum computers and where are we? So let me try to say a little bit about this. And so forgive me if you know a lot about quantum computing. This will be very basic. I'll be asked to cover some basic stuff here, so that's what I do. But you know, what are really these quantum computers and how are they different from classical computers? Well, classical computers, they really work with bits at the very lowest level. And you know, they can only be in 0 or 1. So they're digital and have no value in between. Any value in between 0 and 1 is a mistake. And they have been extremely good at weeding out these mistakes. So today they make no mistakes whatsoever, virtually. And so they're very stable things. They're made out of transistors, of course. And you know, what one does is one uses these transistors to make operations of gates, classical logical gates on these things, and they work extremely well. Now, what about quantum computers? Well, quantum computers has the property that they can, in each of their units, if we're thinking sort of standard qubits, qgates, quantum computers, then each replacement for a bit is a quantum bit. And this quantum bit is really something that can be in any, we call it linear combination between 0 and 1. So it can in fact even be a complex number times 0 plus another complex number times 1 in such a way that the norm squared of the two complex numbers is equal to 1. And this has to do with a probability description of the situation, namely the following. If you measure such a qubit, something very fantastic happens, namely you will only get 0 or 1 as the result of measurement. I don't think anybody in the world really understands why this is the case. It is attributed to Bohr as Bohr's measurement principle. It gives you only a classical result, and it is a probabilistic process, and the absolute value squared of the complex number that's multiplied by 0 gives you the probability of hitting 0, and the absolute value squared of the coefficient in front of 1 gives you the probability of hitting 1. And therefore, they have to sum to 1. So very interestingly, this is the measurement principle, and I actually really don't think we have fully understood and explained why this happens. But the last 130 years experiments in all quantum labs around the world shows this extremely clearly. And now there's of course also quantum operations, quantum gates that can operate on qubits. So they're very much parallel to classical gates, but now they no longer just operate logically, they can actually also produce linear combinations and so on. And this is what causes entanglement. And this is really somehow what actually makes quantum computers much more powerful than classical computers. But there is another aspect to it also, and that is that the power of the quantum computer grows exponentially with the qubits, whereas this is only a linear growth for classical computers. And so this is a totally different thing. When things grow exponentially, this is just a completely different matter. Now, it is not all tasks right now that are super suitable for quantum computers. There is a certain set of problems that one can expect that quantum computers will be use and be able to run and compute with faster than classical computers. And if you look at sort of what mainstream applications of quantum computing, processing of large sets of data and communication and so on, well, that's better handled right now with classical computers, whereas certain things like optimization problems and heavy data analysis or simulations of physical processes that we expect that quantum computers will be much better at. There is a little white box over here in the middle I will return to. But let's just have a look a little bit on, just a few years back history. And I think one of the very important moments in time was actually when Google in 2019 came out with their Singapore quantum processor. It was built to have 54 qubits, but there was one that didn't work, so it had 53 qubits. And what they were saying was that with this machine here, they were able to do some computations that only very large classical computers could do. They were namely doing something called quantum random circuit simulation. And this is known to be super, super hard for classical computers. It is, I would say, at the moment, a mere mathematical game, so it is not something that impresses people in industry. But it is, on a fundamental science level, very, very interesting to verify whether, one can really do something that's much faster than classical computers can do. And so, of course, you're seeing the standard dilution refrigerator here in the picture. The actual quantum processor is not really visible. It's sitting at the very bottom of this dilution refrigerator equipment. And normally this is sunk into liquid helium and being cooled to as close as possible to I think it's about 4 millikelvin at the very bottom to somehow shield it for noise. But, there was after this a big discussion, okay, with IBM, well, was this really so much faster? And, was it really 200 days that it had to run on a classical computer to compare to? And so this was, in a sense, somewhat inconclusive. But let's run time 4 years forward. So in 2023, Google announced an upgrade of their processor to a Sycamore processor with 70 qubits. This made the processor 240 million times more powerful. And at that point, they were computing that Frontier, which was at the time the biggest high-performance classical computer in the world. It's sitting at the Lawrence Livermore National Laboratory in the US in California. It would take it 47 years to do the computation that took the Sycamore computer a second to do. So even though these equipments are noisy and so on, they're still actually doing some very, very impressive computations when you look at it. Something that is out of reach of classical computers, at least on very special tasks. Okay. Oops. Now, so, just to try to sort of show you a few things about quantum algorithms. Okay. So I want to show you sort of very simple-minded sort of explanation of a few different things. I want to relate it to very practical, everyday things that people use in, say, commerce and research and science. So one is, suppose you have a huge amount of big data, and this big data you have gathered on customers from online interactions, many different customers, many different companies, and so on. So maybe you have a huge amount of data. So maybe this number here represents the amount of data that you have in your data base. And now what you want to do based on this data, what you want to do when these customers are surfing the net, and in particular get by your homepage, what you want to do is actually to show them advertisements that are really tailored to your customers. And you also want to give the customers a very good feeling of somehow interacting with the system so that the system recommends what they like. And so this here is a mere application of linear algebra. So huge computer systems every day crank out tons of linear algebra to do this. So maybe we have 1 million customers who then all has all of these features. So there's tons of different things we have to run through. And therefore, it is an enormous amount of times we have to do these computations. And so these computations takes, very long to do on classical computers, but linear algebra can actually be speeded up by an algorithm that's called the HHL algorithm. So it's certain parts of linear algebra that can be done faster. In fact, it can be done exponentially faster. And when you say exponentially faster, you see that the number of operations is going down significantly. So from some very, very large number like this to just merely 21. And therefore, if you have to do this a million times, well, then we're talking about 21 million, as opposed to the huge number you see right here. So this is an instant of this thing that where you were, applying something that has exponential speed up, and it gives a tremendous change. So that we know about on the purely theoretical level right now, but it is a very nice algorithm. It does some aspects of linear algebra exponentially faster. And you see the numbers here in front of you. Now, there is another thing that you can try also, and that's the following thing. Suppose we have a company and we would like to do a resilience analysis on this company. We might have, say, 200 different external conditions for the company. We cannot control these. The answer to these conditions can be, say, digital. They can either be yes or no. And what we would like to do is actually run through our model to determine whether a company is successful, and simply plow through all the possible yes-no combinations we have for these 200 conditions. I mean, 200 conditions is not very many for a large company. And we'd like to run through them and determine by our sort of algorithm that we have determined through lots of internal processes in the company, if we, in all cases of these 200 parameters, actually are successful. Now, the number of possibilities in this case is a gigantic number. I have written an approximation to it right here. This is 2 to the 200 written out in digital form. And so in this case here, it is easy to prove that if we do not have a deeper understanding of what this function does and so on, the only possibility we have is to run through all of the possibilities, test each single one of them, and therefore that would be this amount of times we have to run, and that is absolutely unreachable by any classical computer on Earth at the moment. Impossible. So therefore this cannot be done today. But there is an algorithm, a quantum algorithm called the Dutch-US quantum algorithm. And if we can find an encoding of this function f up here, then something incredible, fantastic happens. Namely, this algorithm is capable of, so to speak, running through all of these possible settings in parallel in one go. So it needs one clock cycle, so it's one pass of this quantum algorithm that you see here, and that will, with probability 1, so deterministically determine whether the answer is yes or no, i.e., do we actually, do we satisfy that we become a success no matter what the 200 inputs are in terms of yes or no. So this is pretty amazing. I mean, this is another instance of where we show, the power of possibilities of quantum computing with exponential speed up. So this was 2 algorithms that we know that have exponential speed up. What's the problem with this? I mean, why are we not sort of hammering away already on this? Maybe most of you already know, but of course it has to do with what I hit here. Classical computers, as I said in the bit in the beginning, they operate fantastically. They don't make any errors. All of this has been cleaned out by 70 years of perfection. Whereas quantum computers, we are still struggling to develop them. They have high error rates at the moment. And that's why we sort of ultra cool them to reduce the scale of those errors, but they do make errors. And so therefore we need to actually, so we cannot run these, algorithms at the moment at this large scale. Okay. But so what we need to do in order to somehow handle these errors is that we have to do one of 2 things, or maybe even both. We need to do error correction. And what one means by error correction is that what one does is one takes a number of physical qubits and then one embeds one logical qubit in the space that these physical qubits represents. So one is embedding some abstract C2, so the complex number squared for 1 qubit, right, into maybe C2 to the m, where m is some number of physical qubits. And there is a number of different, surface code, TQFT codes, all kinds of other parity codes that are popping up at the moment. It's an extremely active, very interesting research area. And the demand for the relation between the number of physical qubits for each logical qubits actually varies quite a lot over different kinds of quantum computing platforms. And so there's lots and lots of interesting stuff going on in actually tailoring various error correction schemes to specific quantum hardware. And the key word here is logical qubit. And so it's slightly misleading, okay? Because logical, you might think that that was something that really performs logically perfect according to the math description of how these things really function, and which I imagine you will learn about at this summer school. But that isn't quite right. I mean, these logical qubits are not perfectly logical qubits. They are really encoded qubits, but they behave much more like logical qubits. And eventually we will actually be able to have a situation where the fidelity of the hardware has grown so high and our ability to correct for mistakes meet each other, and we can actually have codes that perform perfectly at a large scale. We're not quite there yet, but I can tell you it's developing by the day, and it's a very interesting research field. Another possibility is to do error mitigation. That means that you might actually somehow compose your quantum runs with some kind of post-classical computation of some sort. Maybe you are using some kind of AI system to actually try to guess what was it actually that the quantum computer wanted to have done if it was running logically perfect. And so, in fact, the IBM has actually shown the way here in 2023. They took their 127 qubit processor Eagle, and they ran some various things using something called the Ising model that they simulated on this machine. And they were able to show actually that they could train a neural network in such a way that the neural network could actually reproduce the logically correct response from the noisy response that it received. So the interesting thing is neither the quantum computer nor the AI system could function alone, but combined with running the quantum computer, taking the actual output from it, and then inserting it into an AI system allowed them to actually do something that performs as if the whole thing was running completely accurately, logically correct. So it's very interesting. And these two things, I think, will go together in the long run, and we will see lots of applications where classical computers are interacting both for error mitigation, but also for interacting and only using the quantum processor to actually do what's really needed on the quantum processor, and the classical computer does the rest. So there are two sort of ways you can combine classical computing and quantum computing, and for the foreseeable future, I think that the two will run hand in hand. Now, the question is, so where are we today? What's the state of the art in quantum hardware? And so I'm not going to sort of extensively explain to you all of the things that's going on, but let me just tell you sort of what's going on with 4 platforms. So maybe the most common one is the superconducting quantum computers. It's this chandelier figure that we have been discussing before, right? That is this dilution refrigerator insert. And so, IBM, Google, Amazon, and Rigetti, and so on are really Oxford Quantum Circuits and so on are really working on this platform. I think that the leader right now is maybe the Willow processor from Google, which has a 105 physical qubits, and with their system and so on, that translates to about 10 logical qubits. If you look at trapped ions, then I think that it's, you're looking into companies like Quantinuum, IonQ, and I would say probably the leader there is Quantinuum at the moment. They have a very nice setup with their Helios 2 system. And so one big difference between trapped ions and superconducting is that now you store your qubits on individual ions, and you can actually move them around, and you can do all-to-all connectivity. So you can do 2 qubit or gate operations on any 2 qubits by moving them around. That's not possible in superconducting setting. And currently, the setting is that they have about 56 physical qubits, but because of the higher fidelities that are possible on this platform, that translates into about 12 logical qubits. And their preview is that here very soon, Q3, they said, they will have Helios go online, and that will have 96 physical qubits, and they are saying that should translate into about 50 logical qubits. So please hold on to that number, 50 logical qubits. I'll get back to that in a second. If we go to neutral atom quantum computers, I have highlighted here Qpurpose. It's about the same platform as Pascal are using. They're using actually Rydberg states to store the qubits in. Atom computing is slightly different. They are actually using nuclear magnetic spin to store the actual qubits in it, and then they use the Rydberg state to actually interact them, so do the gate operations. And actually, I remember now that I failed to tell you that actually Denmark has just bought an atom quantum computer, which will be delivered in the end of 2026. And that's again the Novo Nordisk Foundation in conjunction with the Danish government actually has done that. But what is the state of that? Well, the state of that right now is that they have about 256 physical qubits. That translates into about 30. But they are saying that they're looking into 10,000 physical qubits, and that should translate to about 100 logical qubits next year. So hold on to these numbers, 100 now. And well, another platform which is less common, very interesting, is the photonic quantum computers. And right now, maybe the leader in that is SDU from Canada. Quandel is also working in this direction, and Orcas also, but they're working on some other platform I'll get back to in a second. But SDU, is really working on, standard full-fledged quantum computing with photonics. They have about 26 qubits, which they are sort of talking about. It translates into 24 logical qubits, but haven't really seen that. So, yes, maybe, I don't know. I'm very surprised about the quotient there. It's somewhat speculative, I think, for now. But anyway, let me try to move on and maybe ask you a little interesting question. So this is a list of the biggest HPC systems in the world. And so the little exercise I'd like you to do right now is so look at this. So I'm not sure whether this is actually completely updated. There might be one that is even bigger than this one here, but only by a small tad bit, I would say. El Capitan used to be the biggest one. Frontier was for a while, then it was El Capitan, and maybe now it has changed to another one. But, it's not by a huge amount of difference. If we go down, we actually also on the list in Denmark, we have a new big HPC classical computer. It's called the Gefion, and it's about the 21st. So my question to you guys, and unfortunately, I just made the mistake of flashing the numbers before. So those of you who are fast saw it. The rest will have to rely on a guess. How many qubits do you think these machines can simulate? And the way that we have computed this is by saying you cannot simulate full-fledged gate interactions on a number of qubits if you cannot just hold the full information of all the qubits in memory. So all what we're doing is actually just computing how much can they hold in memory. And so, of course, it doesn't make sense for 760 people to all shout out a number. So I hope you have made your guess, and then here's the results. So if we're looking at the one we have in Denmark, it can simulate about 41 logical qubits. If it has to do all-to-all connectivity and do really hard stuff like the HHL algorithm I showed you before, or the Deutsch UHAS and so on, which uses a quantum Fourier transform, well, then it hardly can do it, because this is what it can hold in memory, and then it'll take it a very long time to do each of the gates. If it's full interactions in, the unitary group of 2 to the 41. And El Capitan can do a mere 6 qubits more. And so if you have a quantum computer which can do which can handle 50 logical qubits, and it can do a fault-tolerant gate operations on this, there is no computer classical on Earth that can simulate this. And then I just remind you that when we pass 50, we go to 51, 52, and so on. And each time it doubles its capacity. So when we hit 60, it is 2 to the 10 bigger than when we hit 50. And when we hit 100, it is 2 to the 50 times bigger than that. So we are looking into absolutely new uncharted territory of computer capacity once we are at the situation where these quantum computers can operate, error-free on these numbers of qubits. And so I just remind you back here, there are numbers like 50 and 100 qubits being talked about here. Now, there is also the question about gate fidelity and so on, so they are not perfect and so on. But we must say that it is very likely that we are going to see hardware installations that are bordering on what we can actually simulate on classical computers in about a year's time. And it will be very, very interesting to see if people can manage to actually do what's called quantum advantage. And that is, it is doing some computation that some science or some company really cares about and can use and utilize. There's nothing to do with quantum, it's just some problem they care about and would like to solve. And second of all, it is something you can do on a quantum computer, and it completely surpasses what you can do on classical computers. So we are entering into extremely interesting times in this field. Now, these quantum computers, they don't do anything if you don't pour the fuel into them. And the fuel is really actually software. And so I just want to sort of jump over this and go to the next one and say that, no matter where the actual hardware development really goes. And so this here is something I stole from the Japanese Research Institute of a prediction. It involves two predictions. So you see the lower line was the prediction that was a forecast in 2019. The upper line is actually now the forecast in 2024. So actually, we have surpassed the previous prediction, and things are actually evolving faster than we expected. And all of these things really needs very, very careful preparation of mathematical problems that emulates various things that science or industry are interested in, so that it can be turned into precise mathematical problems. And these mathematical problems can then be solved explicitly via quantum software and quantum algorithms on these installations. So the hardware evolution is extremely important. But my maybe very optimistic guess, some would say, but my prediction of this is that actually very soon we'll see the hardware completely outperform the software developments, and we will be lagging behind. So I think there's an enormous need for actually really being very serious about developing lots of new algorithms and really understanding how can we utilize these incredible powers that we are now looking into with these quantum computers. So they cannot do everything, but I think they will do really well on some very specific things like, material physics or quantum chemistry. Also, I think they will do wonders in quantum optimization, so optimizing various things. I think they will have huge impact in finance, in AI. Don't forget that AI right now runs on extremely expensive in terms of energy installations, right? These are these very advanced GPUs that fire up AI, but they use an enormous amount of energy. And that's a fantastic thing about quantum computers. They use a fraction of this energy. A quantum computer uses about as much as you and your family use in your household. An AI system uses maybe what an atomic power plant can produce. So this is an enormous difference, right? So that is also a very strong impetus to actually move to quantum computers in as far as we can possibly make it work. Anyway, I want to shift gear a little bit. And then what I want to do in the remaining 20 minutes of this talk is that I would like to tell you about an algorithm that we have produced and invented. And we worked on this for the last couple of years, and we published the papers in the early spring, in February. And it is joint work together with Associate Professor Xian Shan, who's also at the Center for Quantum Mathematics that we have at SDU. We published two papers. There is 188 pages of math you can enjoy reading. But now let me try to sort of give you an overview about what this is about. And so this is not about standard qubits, qgates. So it's about a very special platform. It is something called Gaussian boson sampling. And so it is something that is realized typically using photonics. So let me try to explain to you what is this photonics installation. So what you should imagine is that you have n sources of laser lights that are being shot into n different optical channels. Excuse me. And what they then go through is something called squeezers. So one squeezes the quadrature of the light. So this is a special sort of optical effect that you do. And then it goes through something called passive optics after that, going through something called beam splitters and phase shifters. And once it's gone through the system, what you do is you do photon counts on the outs. So you count how many photons come out in each channel. And so you can control the settings on the squeezers, and you can control the settings on the phase shifters and the beam splitters. And they are all controlled by a symmetric let's say there are M channels, so it's M by M matrix. This is what I've called B here. This is the B matrix that you see appearing here in some formulae. I'll explain to you in a second. But the output is something like 0 photons detected in the first channel, 0 photons detected in the second channel, 4 detected in the third, 5, 6, 3, 0, 0. And so you keep doing this. And this apparatus can, depending on how good it all is and so on, refire from something like 100,000 times per second to about 100 million per second, depending on how expensive the equipment is. And what you should imagine is that it is a bit like this Japanese game Pachinko, where you have a steel ball that comes out in the top, and then it bounces off some steel rods, and then it falls into some bins at the bottom, and you have to put your money somewhere. And of course, if you put your money in the middle, where the probability is highest, you get the least, and if you put the money out on the side, you get the biggest return. So down here, there is in the quantum world, so it's a quantum Pachinko, if you like, and the hard thing about this is that there is some probability, okay, for each output number, so each sequence of outputs. And these probabilities are given by a certain matrix function. So you do something specific depending on the photon patterns to this matrix, which was an M by M matrix, then you get a much larger matrix, because you basically, anytime, whenever you see a certain number here, you take the corresponding row and column and you double it that many times. If it's 0, you erase it. So you get a larger matrix out of this, whose total size is the number of photons, total number of photons detected. And then this special Hafnian function actually turns into describing the probability for seeing a specific pattern. So all this machine can do is actually efficiently sample this probability distribution. And so you have to understand that whatever you want to do with this, you have to somehow transfer your problem into a problem which you can then sample in this probability distribution or relate to the sampling of this. And I should say that the Hafnian, actually, it's a matrix function. It was invented by quantum field theorists, and it's actually related to these specific integrals here. G is a certain Gaussian function I'll tell you about in a second. And then you're looking at higher moments of this Gaussian, and they are given by these Hafnians. And so they were actually, I think, invented in about the 60s, and it was an Italian physicist who was visiting the Niels Bohr Institute in Copenhagen. And so that's why he called it the Hafnians. Why? Well, because Hafnia is the old Latin word for Copenhagen. And so he called it that. That's why it's called the Hafnians. And he used it not for quantum computing at all. He used it in quantum field theory, but now it resurfaces and has this very interesting role to play in quantum computing. And so this platform was proposed as a very interesting quantum device by Aronson and Akipov some 13, 14 years ago. And then what they showed was that it is insanely difficult to somehow simulate this machine on a classical computer. And that has to do with that computing the Hafnian is extremely hard for classical computers. It is in the complexity class called sharp P hard, and therefore basically impossible to do. But the point was that also people didn't really know, how do we actually use this machinery here for an interesting problem, so we can actually make use of this machinery. And so there has been some ad hoc things done over times, but there hasn't really been a very serious application that you could prove had some kind of speed up. And so that is what we have actually achieved. So what we did was actually to focus on this kind of problems here, to actually compute averages of an arbitrary function, which is here given by a Taylor series, times some Gaussian distribution, which is given by a symmetric n by m matrix like this. And so one wants to compute these mu's here. So now you might say, yeah, that's a very mathematical problem. We know you're a mathematician. You like math problems, are all good. What does that have to do with the rest of the world? Well, to answer that, let me show you this list here. Such integrals here, you can reformulate the following problems in terms of such integrals. Pricing of assets and options and risk factor for financial instruments. So pricing of options, risk factor computations, optimization of power to X systems, weather prediction, optimization in logistics, optimization of clinical drug testing design, new drug design optimization, production optimization, scheduling and planning, and inventory optimizations. The list is longer, but there is a long set of very interesting problems you can actually do if you can do such integrals. Okay, so therefore the whole game is actually to try to use this equipment to do this. And the basic idea is extremely simple. All we are doing is we start with the problem, then we interchange the sum and the integration. And then what you see now by what I showed you before, that the Hafnians are related to these moments of Gaussian distributions. Actually, this mu here rewrites as a sum of Hafnians. And now what you do is you simply just start your Gaussian boson sampler. This will give you all of these photon counts. Each time you get a photon count, you pick up the corresponding Taylor coefficient, and then you start summing the Taylor coefficients. And so this is a new way of computing these integrals. The standard way of computing them is really to sample the function according to this distribution. That's called Monte Carlo simulation. And there is tons of Monte Carlo simulation being done on a daily basis, and all of these problems here to solve them. So the whole question is, how does Monte Carlo simulation compare to this new Gaussian boson sampling method? And our main result of these two papers that I told you about before is that we can actually prove that under certain specific conditions, we get exponential speed up over Monte Carlo simulation. So it is another one of these quantum algorithms, which I should say very rare. We only knew 3 quantum algorithms before this, and this is the 4th one, which offers exponential speed up, guaranteed by proof. But you can easily see it in various examples. So here's an example where we start sampling the problem, and the red curve is the Gaussian boson sampling, and the blue curve is Monte Carlo simulation. So you see very quickly we find the true value for this integral with the Gaussian boson sampling process, whereas the Monte Carlo is all over the place and it takes a very, very long time before it converges. Here's another example. Okay, the Monte Carlo gets close, but we don't know the value, right? So it starts deviating off again. And then, as I said, there are certain conditions for us to be able to prove that there is exponential speed up. But then we actually did the following. We also tested in the entire space how many % of the space in these Gaussian weighted integrals can we actually do better with Gaussian boson sampling over Monte Carlo simulation. And you can see that unless the what you see here is the degree in the Taylor coefficients, and here you see the dimensions of the integrals grow. And as soon as you're just away from the first few Taylor coefficients and more asking for more precision, you are guaranteed that at 100% of the time, you will succeed with Gaussian boson sampling much faster than you can with Monte Carlo simulation. And how much faster depends on how much precision you ask for. So this algorithm is really in practice much faster. And actually, sometimes we are lucky that we can actually sample this and simulate it on classical HPC systems. Of course, we cannot scale this to very large, high degrees of integrals, so many dimensions and high Taylor degrees, because that's the theorems by Aronson and Qpurpose. We know we cannot do this, but in the lower scales, we can actually use it and more efficiently compute various integrals in low dimension and low Taylor degree, where we can actually put the Hafnians on HPC systems. And so this here new machinery, we have actually tried to put to the test. So maybe I just show you one of these pixie explanations again. So one of the real serious applications of this is to predict price evolution of, say, important financial instruments very precisely. And so the number of Monte Carlo runs that you have to do is gigantic if you want a very precise estimate. But because of our exponential speed up, we need something of the order of 100,000 times. And this is something you can do in the terms of a second or two on a physical installation. And if you do the preparation of all of the computation of the Hafnians, you can do it in a fraction of a millisecond on a classical computer. The real computation time goes into computing these Hafnians. That takes a long time. But the nice thing is that there is sort of a separation between the Hafnians, as I showed you here. Oh, sorry, it's up here. So you can actually, the day before, compute the Hafnians if you fix the B. And then if you have new problems where varying Taylor coefficients, well, then you can do that extremely fast on a classical computer. And so that's actually what we're doing when we're using these techniques to, improve predictions of financial instruments. And so actually, I want to tell you a little bit explicitly about this because I just want to end the talk by showing you some of the things that we're doing for industry in our collaboration directly with them. We believe that this is going to influence all of industry, not just our algorithms, but quantum computing and quantum algorithms in general. There is a really fantastic, bright future ahead of us, I think. And I just tell all you young people, whoa, you live in extremely fantastic, interesting times where you are going to see and work and do actually spreading quantum computing over the entire sector of all kinds of industry and science. It's going to be an exciting time, I would say. I really look forward to watching some of this, being part of it in the beginning and seeing how it is going to evolve. But so for us, we're already engaged in actually doing it directly. So with one of the biggest banks in Denmark called Jyske Bank, we're actually doing this. So we have software that runs on their trading desks. We have had it run since September last year, and it has consistently every day done performance. I'll show you one specific day from one of the first days where we started working with them. So that's the 17th of September 2024. And what we're doing here is a certain specific financial instrument. We have to hit all the red marks here, and it's the beginning of the red marks that we have to hit. And what we are showing is that with a mean of less than 2 base points, and 2 base points means 2 divided by 10,000, we can predict the evolution just a few minutes ahead to a few seconds to a few milliseconds, depending on the instrument. But this is enough for them to trade it, and the result has been consistent throughout. And so been running a proof of concept project with them, but they have just recently announced that they want to actually turn this into a very solid collaboration with us and scale by a factor of 10 and so on. So that's really exciting. And in fact, we was features at one of the sort of specific use cases of quantum in a sort of little folder that the government produced of interesting use cases. And I should say that actually we are the only one who actually was able to produce a use case which actually is in use. So the trading floor, this is a picture from the bank, and the trading floor that uses is the ones that are sitting behind the yellow mark here. And actually now the biggest bank in Denmark would like us to do the same with them. And so we are starting to engage with them. This can also be used for Power-to-X optimization. So that's something we're doing together with the biggest energy company in Denmark called Ørsted. Some of you might actually recognize the name Ørsted. So I don't know if you know, but Ørsted was the first to discover the interaction between electricity and magnetism. He did so in 1820. And so it was way before Faraday and all of these people and Maxwell and so on. And so, yeah, that's actually, they took the name from him. They are energy producers, that they rely on this effect by generating electricity from motion of magnets, right, from generators. But of course, we also rely on that for producing electricity if we go out and use wind energy. And this is a huge thing in Denmark with a lot of people engaging in this. We get over 60% of our energy from wind in Denmark today. And what we really want to do is to actually utilize this efficiently. And the thing is, it's not always that we need the energy when the wind blows. So we need to do something to store it. And here, one of the mechanisms is to turn the electricity into hydrogen, store that. Hydrogen can in turn be made into, ammonium. Ammonium can be made into various biofuels, jet fuels, and so on. And so how to optimize these systems is a highly complicated dynamical system that you need to work a lot on. it is classically very, very hard, and we have developed some Gaussian boson sampling algorithms to optimize the system, and we are working on deploying this together with them. So it's a very interesting, different application in finance. And we're doing the same thing with another company in Denmark called the EnergyNet. They are the ones who run the whole system in Denmark of the net and so on, and sells and buys electricity and so on. In terms of weather predictions, we are doing some studies together with the Danish Meteorological Institute. Of course, modeling the weather has to do with solving the Navier-Stokes equation. The Navier-Stokes equation is a very complicated PDE, which is nonlinear. So one has to be very smart if one wants to put that on a quantum computer, which is basically linear progression. But there is something called Kalaman linearization that enables such things to happen. And so we're working together with them on using basic quantum computing in trying to solve these PDEs, and further also to use quantum machine learning to enhance something called parameterization in climate models, because of course they cannot solve the models really by solving the Navier-Stokes equations, in continuous variables over the atmosphere. They discretize the whole thing, and therefore they have to somehow parameterize a lot of the different processes that go on in the atmosphere differently. And so we're also working together with them on this. And I should say that our work on these Navier-Stokes equations, of course, what's interest Rolls-Royce as well, where they want to study this in the context of jet engines. Then there is until lately, the biggest company in Denmark, Novo Nordisk. They have hired us to do the entire quantum roadmap for the entire company. And so we're doing lots of different things together with them. We are looking into molecular docking and developing new drugs. We're looking into pharmacokinetics of such drugs. How do they actually distribute in your body when they get in there? How are they absorbed and so on? It has to do with how much do we have to inject and so on. Also, we are looking into how to actually do route and network optimization for and backorder things and so on. And we're using it also to develop tools to do market analysis together with them. And primarily, we are using advanced mathematics, and then we gradually turn these into quantum algorithms. And several of these things also using this Gaussian boson sampling I told you about earlier. This is our new algorithm. And so somehow this is spread over the entire value chain of the company, from the very early research all the way over to actually post-sales and so on, and to understanding how can one use drugs for other things than they were designed for in the beginning. We believe quantum computing can be applied all over their value chain, and that's something Novo shares with us, that belief. And yeah, I've already said a few things about that. We're doing early stuff with drug discovery, understanding how to actually take and select a specific chemical compound that will actually bind to a specific protein. So many different diseases. We know exactly which protein in the human body is misfunctioning. We know what its active site is, and we simply just have to devise a chemical compound that inhibits the protein, and then we can actually solve, in principle, the disease. This is the way that several new advanced drugs work, but it's very, very difficult to figure out which actual chemical compound binds to that protein and no other protein in the body, so that we don't have side effects. And so that is an ongoing research. It has been going on with classical computers for 50 years. And now we are trying to understand how does that change the landscape with quantum computing and so on. And this looks like it has a very good preview. And of course, what one would like to do is simply to compute which molecule is it that fits in the pocket. And then one would avoid really, really extremely long processes. And also one has to understand, is the molecule toxic and so on. And that one can also do something about on quantum computing. And then there's the whole clinical trial and optimization of that. That's a huge thing for them. And then there's the whole thing about back orders. You cannot have back orders as a medical company. If you go in and say, we would like to supply medicine to sick people in the country, you have to make sure you can deliver. Can't accept back orders, right? And then we're also working with a number of logistics companies where logistics is an obvious thing to also do optimization on. There's so many different problems. The way that we interact with these all different kinds of companies is really by actually going to them, talking to them, understanding their problems. Then we go back, develop advanced mathematical models, typically do something that's more advanced than they normally have access to. Then we present that for them. If they like the idea, they go on with us, and we build quantum solutions for them that can well, in first instance, be simulated on classical computers, eventually run on quantum computers when they're ready. And then we actually build it into their production if this is successful, as we have been with Jyske, as I showed you earlier, and Novo Nordisk. So yeah, this is my talk. I wish you a really, really great, summer school. Let me say again, I think you're headed into a world of quantum computing, which is more exciting than anything I could imagine the last 200 years. Thank you very much for your attention.
Thank you very much, Jørgen, for this fantastic and amazing conference talk. I think we have time for a couple of questions. Is there anyone who wants to pose a question to Jørgen? Please, you can do it in Spanish and I will translate.
Thank you so much, Dr. Jørgen. The question is related to the business side, because for enterprises in Latin America, maybe traditional data science experimentation may imply high cost. Based on your experience, how many times those quantum experimentation costs compared with traditional definition of algorithms on classic compute? And I'm not sure if there is any measure of the net profitability for those projects.
Yes, so thank you very much for the question. So it involves various aspects, but one of them, which was the last one, maybe I can pick up on that. So, these people from the bank, there's one thing that counts for them. And that is if you make money or not. So they tested for about 10 months whether they see that they can make money on this. And so they can make money on this, and that's why they decided to move on. So this is profitable. And that's also why we now engage with another bank in Denmark, and we intend to actually go to the banks in the world after we have somehow really instrumentalized this and made it a package we could sell. And so here it's a matter of doing something which is very new and thinking very differently, and it's not available today via classical solutions. So the answer there is it's profitable, and it wasn't available using classical tools before. So you need some version of quantum. It was quantum mathematics to begin with. And of course, if we want to scale it to very large equity classes and markets and so on, we will need quantum computers. There's no way around it. But there is really a use case here which shows that this you cannot do. So I think that's another message. We should also try to think about what can we actually do with these new quantum computers. That's another message. You also talked about what about if we don't have much data and so on. Well, you will be surprised that some of the finance industry has a lot of data, but there are other industries that have way less data. So these people here don't have so much data, but they have a very hard computational problem. And so that we were also able to somehow solve for them. And so this means that they can now actually do lots more studies of what will happen, if we have this adverse condition. What happens if all of a sudden the prices falls to 20% of what they are today? How will this affect our business and so on? These adverse events that are hard to do when you just do average computations, they are available. So yeah, I mean, this is, there are possibilities for this, even if you do not have a lot of data assembled. Of course, there are other cases where it's really great to have a lot of data. But I should also say that having a lot of data, yes, it's not always easy to combine that with quantum computing nowadays, right? Because you cannot feed a lot of data through a quantum computer somehow. Not yet. So you need to really find some kind of hardcore problem that can be solved using the quantum methods, which cannot be solved on classical computers. And so this requires that a team of strong quantum mathematicians team up with a team of domain experts from the company and really set their mind to actually solving some problems. It took us 2 years to work with these guys, and it took us 2 years to work with the people in the bank to actually make a difference.
Thank you so much.
We have a question from people on backstage.
Okay, it says, you say that Denmark will have a quantum computer by 2034, if successful. They'll have more than 1 million quantum gates, or am I wrong? If so, how is it that in 2023, Google only had 70? What is the key difference in terms of gate numbers? Is it a budget issue, or is it more related to a physical one trying to keep those very low temperatures?
Well, all of the above. But so the numbers were that in 2034, so in the future, right? In 8 years from now, something like this, 9 years, they are hoping to have a quantum computer with 1 million qubits, which can operate on that 1 million qubits logically correct, basically to an arbitrary gate depth. So they are hoping to have a situation where they can error correct on this monster in such a way that they can run an arbitrary number of gates. I think none of us can imagine what kind of computations you can do with such an equipment if it really can be built. It's a very bold, fantastic thing that they are doing. They have various special experts on various things. Will they succeed where others won't? I don't know. You know, I think it's going to be a race. I think that actually these amounts of money are maybe not enough. I think that big international companies like Google and IBM and so on are maybe putting in a factor of 10 more than this. So I think it takes a lot more. And as far as I can tell so far, actually the American big companies and a couple of in Europe are more successful at doing this at the moment. But these people are sort of more on the research side, and they really want to use the quantum computer to solve this docking of ligands to proteins. And if you really want to do that in a biological relevant context, you're looking maybe, some estimates say, at around 1 million qubits and then an arbitrary number of gate operations on these. I hope this answers.
One last question, Jørgen. What is the dimension of the problems that you are solving when you talk about these projects on predicting financial landscapes? How many variables do you have to deal with, and in which platform do you run these problems?
So we run it on an HPC system we have at the university where we are working. And it's basically doing things of the order of 2 to the 30.
2 to the
2 to the 30. So it corresponds to running a quantum computer with 2 to the 30, so 30 qubits. That's a rough translation because we're not using qubits and qgates, we're using Gaussian boson sampling. But I would say that it's equivalent to simulating a 30 qubit quantum computer, what we do. So what we are doing is we are computing all of these Hafnians. So all of these guys here, right? And so we do that overnight using our HPC system. And so there is an explicit formula for computing these, and there are actually efficient algorithms to approximating them additively up to a certain size. And then we have those, and then during the day, the Taylor coefficients are affected by the trades. And so therefore we have stored these and have them available. We just need to feed in the new Taylor coefficients and do this sum here, and that can be done extremely efficient on a classical small computer during day trading. So that's done on the bank's system during day. But it's a large sum, this one here, okay? So imagine you have a 30-dimensional integral here. It's a really large sum, but it's something a classical large computer can do very fast. But it cannot compute the Hafnians very fast, and that takes all night on our system or our large, classical computer system.
Mhm. Thank you very much for your answer. I think we have to stop now, Jørgen. I thank you very much on behalf of the National University of Mexico. I really thank you for this exceptional keynote. We'll be sending you your certificate of participation, and once again, thank you very much.